The Universe Around Us. James Jeans. Introduction. The Study of Astronomy. On the evening of January 7th, 1610, a fateful day for the human race, Galileo Galilei, professor of mathematics in the University of Padua, sat in front of a telescope he had made with his own hands. More than 3 centuries previously, Roger Bacon, the inventor of spectacles, had explained how a telescope could be constructed so as to make the stars appear as near as we please. He had shown how a lens could be so shaped that it would collect all the rays of light falling on it from a distant object, bend them until they met in a focus, and then pass them on through the pupil of the eye onto the retina. Such an instrument would increase the power of the human eye, just as an ear trumpet increases the power of the human ear by collecting all the waves of sound which fall on a large aperture, bending them and passing them through the orifice of the ear onto the eardrum. Yet it was not until 1608 that the first telescope had been constructed by Lippershey, a Flemish spectacle maker. On hearing of this instrument, Galileo had set to work to discover the principles of its construction, and had soon made himself a telescope far better than the original. His instrument had created no small sensation in Italy. Such extraordinary stories had been told of its powers that he had been commanded to take it to Venice and exhibit it to the Doge and Senate. The citizens of Venice had then seen the most aged of their senators climbing the highest bell towers to spy through the telescope at ships which were too far out at sea to be seen at all without its help. The telescope admitted about 100 times as much light as the unaided human eye, and, according to Galileo, it showed an object at 50 miles as clearly as if it were only 5 miles away. Perhaps it need hardly be said that this is quite insignificant in comparison with the power of modern instruments. The telescope of 100-inch aperture at Mount Wilson, California, the largest at present in existence, admits 2,500 times as much light as Galileo's tiny instrument, and so 250,000 times as much light as the unaided eye. It is hoped that a 200-inch telescope will shortly be built in California. This will admit 4 times as much light as the 100-inch instrument, or about 1,000,000 times as much light as the unaided eye. The absorbing interest of his new instrument had almost driven from Galileo's mind a problem to which he had at one time given much thought. Over 2,000 years previously, Pythagoras and Philolaus had taught that the Earth is not fixed in space, but rotates on its axis every 24 hours, thus causing the alternation of day and night. Aristarchus of Samos, perhaps the greatest of all the Greek mathematicians, had further maintained that the Earth not only turned on its axis, but also described a yearly journey round the sun, this being the cause of the cycle of the seasons. Then these doctrines had fallen into disfavor. Aristotle had pronounced against them, asserting that the Earth formed a fixed center to the universe. Later, Ptolemy had explained the tracks of the planets across the sky in terms of a complicated system of cycles and epicycles. The planets moved in circular paths around moving points, which themselves moved in circles around an immovable Earth. The Church had given its sanction and active support to these doctrines. Indeed, it is difficult to see what else it could have done, for it seemed almost impious to suppose that the great drama of man's fall and redemption, in which the Son of God had himself taken part, could have been enacted on any lesser stage than the very center of the universe. Yet, even in the Church, the doctrine had not gained universal acceptance. Oresme, Bishop of Lisieux, and Cardinal Nicholas of Cusa had both declared against it, the latter writing in 1440, "I have long considered that this earth is not fixed, but moves as do the other stars. To my mind, the earth turns upon its axis once every day and night." At a later date, those who held these views incurred the active hostility of the Church, and in 1600 Giordano Bruno was burned at the stake. He had written, "It has seemed to me unworthy of the divine goodness and power to create a finite world, when able to produce beside it another and others infinite, so that I have declared that there are endless particular worlds similar to this of the earth. With Pythagoras I regard it as a star, and similar to it are the moon, the planets, and other stars, which are infinite in number, and all these bodies are worlds. The most weighty attack on orthodox doctrine had, however, been delivered neither by theologians nor philosophers, but by the Polish astronomer Nicholas Copernicus, 1473 to 1543. In his great work De Revolutionibus Orbium Coelestium, Copernicus had shown that Ptolemy's elaborate structure of cycles and epicycles was unnecessary, because the tracks of the planets across the sky could be explained quite simply by supposing that the Earth and the planets all moved round a fixed central sun. The 66 years which had elapsed since this book was published had seen these theories hotly debated, but they were still neither proved nor disproved. Galileo had already found that his new telescope provided a means of testing astronomical theories. As soon as he had turned it on to the Milky Way, a whole crowd of legends and fables as to its nature and structure had vanished into thin air. It proved to be nothing more than a swarm of faint stars scattered like golden dust on the black background of the sky. Another glance through the telescope had disclosed the true nature of the moon. It had on it mountains which cast shadows, and so proved, as Giordano Bruno had maintained, to be a world like our own. What if the telescope should now in some way prove able to decide between the orthodox doctrine that the Earth formed the hub of the universe and the new doctrine that the Earth was only one of a number of bodies, all circling round the sun like moths round a candle flame? And now Galileo catches Jupiter in the field of his telescope and sees four small bodies circling around the great mass of the planet, like moths round a candle flame. What he sees is an exact replica of the solar system as imagined by Copernicus, and it provides direct visual proof that such systems are at least not alien to the architectural plan of the universe. On January 30th, he writes to Belisario Vinter that these small bodies move round the far greater mass of Jupiter, just as Venus and Mercury, and perhaps the other planets, move round the Sun. Any lingering doubts that Galileo may have felt as to the significance of his discovery are removed 9 months later when he observes the phases of Venus. Venus might have been self-luminous, in which case she would always appear as a full circle of light. If she were not self-luminous but moved in a Ptolemaic epicycle, then, as Ptolemy had himself pointed out, she could never show more than half her surface illuminated. On the other hand, the Copernican view of the solar system required that both Venus and Mercury should exhibit phases like those of the moon, their shining surfaces ranging in appearance from crescent shape through half-moon to full moon, and then back through half-moon to crescent shape. That such phases were not shown by Venus had indeed been urged as an objection to the Copernican theory. Galileo's telescope now shows that, as Copernicus had foretold, Venus passes through the full cycle of phases, so that, in Galileo's own words, we are now supplied with a determination most conclusive and appealing to the evidence of our senses of two very important problems which up to this day have been discussed by the greatest intellects with different conclusions. One is that the planets are not self-luminous. The other is that we are absolutely compelled to say that Venus, and Mercury also, revolve around the Sun, as do also all the rest of the planets, a truth believed indeed by the Pythagorean school, by Copernicus, and by Kepler, but never proved by the evidence of our senses, as is now proved in the case of Venus and Mercury. These discoveries of Galileo made it clear that Aristotle, Ptolemy, and the majority of those who had thought about these things in the last 2,000 years had been utterly and hopelessly wrong. In estimating his position in the universe, man had up to now been guided mainly by his own desires and his self-esteem. Long fed on boundless hopes, he had spurned the simpler fare offered by patient scientific thought. Inexorable facts now dethroned him from his self-arrogated station at the center of the universe. Henceforth he must reconcile himself to the humble position of the inhabitant of a speck of dust, and adjust his views on the meaning of human life accordingly. The adjustment was not made at once. Human vanity, reinforced by the authority of the Church, contrived to make a rough road for those who dared draw attention to the Earth's insignificant position in the universe. Galileo was forced to abjure his beliefs. Well, on into the 18th century, the ancient University of Paris taught that the motion of the Earth round the Sun was a convenient but false hypothesis, while the newer American universities of Harvard and Yale taught the Ptolemaic and Copernican systems of astronomy side by side as though they were equally tenable. Yet men could not keep their heads buried in the sand forever, and when at last its full implications were accepted, the revolution of thought initiated by Galileo's observations of January 7th, 1610, proved to be the most catastrophic in the history of the race. The cataclysm was not confined to the realms of abstract thought. Henceforth, human existence itself was to appear in a new light, and human aims and aspirations would be judged from a different standpoint. This oft-told story has been told once again in the hope that it may serve to explain some of the interest taken in astronomy today. The more mundane sciences prove their worth by adding to the amenities and pleasures of life, or by alleviating pain or distress, but it may well be asked what reward astronomy has to offer. Why does the astronomer devote arduous nights and still more arduous days to studying the structure, motions, and changes of bodies so remote that they can have no conceivable influence on human life? In part, at least, the answer would seem to be that many have begun to suspect that the astronomy of today, like that of Galileo, may have something to say on the enthralling question of the relation of human life to the universe in which it is placed, and on the beginnings, meaning, and destiny of the human race. Bede records how, some 12 centuries ago, human life was compared in poetic simile to the flight of a bird through a warm hall in which men sit feasting, while the winter storms rage without. The bird is safe from the tempest for a brief moment, but immediately passes from winter to winter again. So man's life appears for a little while, but of what is to follow, or of what went before, we know nothing. If, therefore, a new doctrine tells us something certain, it seems to deserve to be followed. These words, originally spoken in advocacy of the Christian religion, describe what is perhaps the main interest of astronomy today. Man, only knowing, life's little lantern between dark and dark, wishes to probe further into the past and future than his brief span of life permits. He wishes to see the universe as it existed before man was, as it will be after the last man has passed again into the darkness from which he came. The wish does not originate solely in mere intellectual curiosity, in the desire to see over the next range of mountains, the desire to attain a summit commanding a wide view, even if it be only of a promised land which he may never hope himself to enter. It has deeper roots and a more personal interest. Before he can understand himself, man must first understand the universe from which all his sense perceptions are drawn. He wishes to explore the universe, both in space and time, because he himself forms part of it and it forms part of him. We may well admit that science cannot at present hope to say anything final on the questions of human existence and human destiny, but this is no justification for not becoming acquainted with the best that it has to offer. It is rare indeed for science to give a final yes or no answer to any question propounded to her. When we are able to put a question in such a definite form that either of these answers could be given in reply, we are generally already in a position to supply the answer ourselves. Science advances rather by providing a succession of approximations to the truth, each more accurate than the last, but each capable of endless degrees of higher accuracy. To the question, where does man stand in the universe? The first attempt at an answer, at any rate in recent times, was provided by the astronomy of Ptolemy. At the center, Galileo's telescope provided the next, and incomparably better, approximation. Man's home in space is only one of a number of small bodies revolving round a huge central sun. 19th century astronomy swung the pendulum still further in the same direction, saying, "There are millions of stars in the sky, each similar to our sun, each doubtless surrounded, like our sun, by a family of planets on which life may be kept in being by the light and heat received from its sun." 20th century astronomy suggests, as we shall see, that the 19th century had swung the pendulum too far. Life now seems to be more of a rarity than our fathers thought, or would have thought, if they had given free play to their intellects. We are setting out to explain the approximation to the truth provided by 20th century astronomy. No doubt it is not the final truth, but it is a step on towards it, and unless we are greatly in error, it is very much nearer to the truth than was the teaching of 19th century astronomy. It claims to be nearer the truth, not because the 20th century astronomer claims to be better at guessing than his predecessors of the 19th century, but because he has incomparably more facts at his disposal. Guessing has gone out of fashion in science. It was at best a poor substitute for knowledge, and modern science, eschewing guessing severely, confines itself, except on very rare occasions, to ascertained facts and the inferences which, so far as can be seen, follow unequivocally from them. It would of course be futile to pretend that the whole interest of astronomy centers round the questions just mentioned. Astronomy offers at least three other groups of interest which may be described as utilitarian, scientific, and aesthetic. At first, astronomy, like other sciences, was studied for mainly utilitarian reasons. It provided measures of time and enabled mankind to keep a tally on the flight of the seasons. It taught him to find his way across the trackless desert, and later across the trackless ocean. In the guise of astrology, it held out hopes of telling him his future. There was nothing intrinsically absurd in this, for even today the astronomer is largely occupied with foretelling the future movements of the heavenly bodies, although not of human affairs. A considerable part of the present book will consist of an attempt to foretell the future and predict the final end of the material universe. Where the astrologers went wrong was in supposing that terrestrial empires, kings and individuals formed such important items in the scheme of the universe that the motions of the heavenly bodies could be intimately bound up with their fates. As soon as man began to realize, even faintly, his own insignificance in the universe, astrology died a natural and inevitable death. The utilitarian aspect of astronomy has by now shrunk to very modest proportions. The national observatories still broadcast the time of day and help to guide ships across the ocean, but the center of astronomical interest has shifted so completely that the remotest of nebulae arouse incomparably more enthusiasm than clock stars, and the average astronomer totally neglects our nearest neighbors in space, the planets, for stars so distant that their light takes hundreds, thousands, or even millions of years to reach us. Recently, astronomy has acquired a new scientific interest through establishing its position as an integral part of the general body of science. The various sciences can no longer be treated as distinct. Scientific discovery advances along a continuous front which extends unbroken from electrons of a fraction of a millionth of an inch in diameter to nebulae whose diameters are measured in hundreds of thousands of millions of miles. A gain of astronomical knowledge may add to our knowledge of physics and chemistry, and vice versa. The stars have long ago ceased to be treated as mere points of light. Each is now regarded as an experiment on a heroic scale, a high-temperature crucible in which nature herself operates with ranges of temperature and pressure far beyond those available in our laboratories, and permits us to watch the results. In so doing, we may happen upon properties of matter which have eluded the terrestrial physicist, owing to the small range of physical conditions at his command. For instance, matter exists in nebulae with a density at least 1,000,000 times lower than anything we can approach on Earth, and in certain stars at a density nearly 1,000,000 times greater. How can we expect to understand the whole nature of matter from laboratory experiments in which we can command only one part in 1,000,000,000 of the whole range of density known to nature? Yet for each one who feels the purely scientific appeal of astronomy, there are probably a dozen who are attracted by its aesthetic appeal. Many, even of those who seek after knowledge for its own sake, driven by that intellectual curiosity which provides the fundamental distinction between themselves and the beasts, find their main interest in astronomy as the most poetical and the most aesthetically gratifying of the sciences. They want to exercise their faculties and imaginations on something remote from everyday trivialities, to find an occasional respite from the long littleness of life, and they satisfy their desires in contemplating the serene immensities of the outer universe. To many, astronomy provides something of the vision without which the people perish. Before proceeding to describe the results of the modern astronomer's survey of the sky, let us try to envisage in its proper perspective the platform from which his observations are made. Later on, we shall see how the Earth was born out of the Sun, something like 2,000 million years ago. It was born in a form in which we should find it hard to recognize the solid Earth of today, with its seas and rivers, its rich vegetation and overflowing life. Our home in space came into being as a globe of intensely hot gas on which no life of any kind could either gain or retain a foothold. Gradually, this globe of gas cools down, becoming first liquid, then plastic. Finally, its outer crust solidifies, rocks and mountains forming a permanent record of the irregularities of its earlier plastic form. Vapors condense into liquids, and rivers and oceans come into being, while the permanent gases form an atmosphere. Gradually, the Earth assumes a condition suited to the advent of life, which finally appears, we know not how, whence, or why. It is not easy to estimate the time since life first appeared on Earth, but it can hardly have been more than a small fraction of the whole 2,000 million years of the Earth's existence. Still, there was probably life on Earth at least 300 million years ago. The first life appears to have been wholly aquatic, but gradually fishes changed into reptiles, reptiles into mammals, and finally man emerged from mammals. The evidence favors a period of about 300,000 years ago for this last event. Thus, life has inhabited the Earth for only a fraction of its existence, and man for only a tiny fraction of this fraction. To put it in another way, the astronomical timescale is incomparably longer than the human timescale. The generations of man, and even the whole of human existence, are only ticks of the astronomer's clock. Most of the 10,000 or so of generations of men who connect us up with our ape-like ancestry must have lived lives which did not differ greatly from those of their animal predecessors. Hunting, fishing, and warfare filled their lives, leaving but little time or opportunity for intellectual contemplation. Then, at last, man began to awake from his long intellectual slumber and, as civilization slowly dawned, to feel the need for occupations other than the mere feeding and clothing of his body. He began to discover revelations of infinite beauty in the grace of the human form, or the play of light on the myriad smiling sea, which he tried to perpetuate in carefully chiseled marble or exquisitely chosen words. He began to experiment with metals and herbs, and with the effects of fire and water. He began to notice and try to understand the motions of the heavenly bodies, for to those who could read the writing in the sky, the nightly rising and setting of the stars and planets provided evidence that beyond the confines of the earth lay an unknown universe built on a far grander scale. In this way, the arts and sciences came to earth, bringing astronomy with them. We cannot quite say when, but compared even with the age of the human race, they came but yesterday, while in comparison with the whole age of the earth, their age is but a twinkling of the eye. Scientific astronomy, as distinguished from mere stargazing, can hardly claim an age of more than 3,000 years. It is less than this, since Pythagoras, Aristarchus, and others explained that the earth moved around a fixed sun. Yet the really significant figure for our present purpose is not so much the time since men began to make conjectures about the structure of the universe as the time since they began to unravel its true structure by the help of ascertained fact. The important length of time is that which has elapsed since that evening in 1610, when Galileo first turned his telescope onto Jupiter, a mere 3 centuries or so. When the various figures are displayed in this form, we see what a very recent phenomenon astronomy is. Its total age is only 100th part of the age of man, only 100,000th part of the time that life has inhabited the earth. During 99,999 parts out of the 100,000 of its existence, life on Earth was hardly concerned about anything beyond the Earth. But whereas the past of astronomy is to be measured on the human timescale, 100 generations or so of men, there is every reason to expect that its future will be measured on the astronomical timescale. We shall discuss the probable future stretching before the human race in a later chapter. For the moment, It is not unreasonable to suppose that this future will probably be terminated by astronomical causes, so that its length is to be measured on the astronomical timescale. As the Earth has already existed for 2,000 million years, it is a priori reasonable to suppose that it will exist for at least something of the order of 2,000 million years yet to come, and humanity and astronomy with it. Actually, we shall find reasons for expecting it to last far longer than this. But if once it is conceded that its future life is to be estimated on the astronomical timescale, no matter in what exact way, we see that astronomy is still at the very opening of its existence. This is why its message can claim no finality. We are not describing the mature convictions of a man so much as the first impressions of a newborn babe which is just opening its eyes. Even so, they are better than the idle, introspective dreamings in which it indulged before it had learned to look around itself and away from itself. And so we set out to learn what astronomy has to tell us about the universe in which we live our lives. Our inquiry will not be entirely limited to this one science. We shall call upon other sciences, physics, chemistry, and geology, as well as the more closely allied sciences of astrophysics and cosmogony, to give help, when they can, in interpreting the message of observational astronomy. The information we shall obtain will be fragmentary. If it must be compared to anything, let it be to the pieces of a jigsaw puzzle. Could we get hold of all the pieces, they would, we are confident, form a single complete consistent picture, but many of them are still missing. It is too much to hope that the incomplete series of pieces we have already found will disclose the whole picture, but we may at least collect them together, arrange them in some sort of methodical order, fit together pieces which are obviously contiguous, and perhaps hazard a guess as to what the finished picture will prove to be when all its pieces have been found and finally fitted together. Chapter 1. Exploring the Sky. We have seen how man, after inhabiting the earth for 300,000 years, has within the last 300 years, the last 1,000th part of his life on earth, become possessed of an optical means of studying the outer universe. In the present chapter, we shall try to describe the impressions he has formed with his newly awakened eyes. The description will be arranged in a very rough chronological order. This is also an order of increasing telescopic power, or again of seeing further and further into space, so that our order of arrangement might equally be described as one of increasing distance from the sun. We shall not attempt any sort of continuous record, but shall merely mention a few landmarks so as to show in broad outline the order in which territory was won and consolidated in man's survey of the universe. The solar system. We may conveniently start with the solar system, the structure of which was unraveled by Galileo and his successors. The Sun's family of planets falls naturally into distinct groups. Near to the Sun are the four small planets, Mercury, Venus, the Earth, and Mars. At much greater distances are the four great planets, Jupiter, Saturn, Uranus, and Neptune. Beyond all these is the newly discovered planet Pluto, the outermost member of our system so far known. Mercury is nearest of all to the Sun. Next comes Venus. The orbits of these two planets lie between the Earth's orbit and the Sun. As seen from the Earth, these planets appear to describe relatively small circles round the Sun, and so must necessarily appear near to the Sun in the sky. As a consequence, they can only be seen either in the early morning, if they happen to rise just before the Sun, or in the evening, if they set after the Sun. The ancients, not altogether recognizing that the same planets could appear both as morning and evening stars, gave them different names according as they figured as the one or the other. As a morning star, Venus was called Phosphoros by the Greeks, and Lucifer by the Romans. As an evening star, it was called Hesperus by both. Next, beyond the Earth, proceeding outward from the Sun into space, comes Mars, completing the group of small planets. Mars, Venus, and Mercury are all smaller than the Earth in size, although Venus is only slightly so. There is a wide gap between the orbit of Mars, the last of the small planets, and that of Jupiter, the first of the great planets. This is not empty. It is occupied by the orbits of thousands of tiny planets known as asteroids. None of these approaches the Earth in size. Ceres, the largest, is only 480 miles in diameter, and only 4 are known with diameters of more than 100 miles. The planets Mercury, Venus, and Mars have all been known from remote antiquity, but the asteroids only entered astronomy with the 19th century, Ceres, the first and largest, having been discovered by Piazzi on January 1st, 1801. Beyond the asteroids come the 4 great planets Jupiter, Saturn, Uranus, and Neptune, all of which are far larger than the Earth. Jupiter, the largest, has, according to Sampson, a diameter of 88,640 miles, or more than 11 times the diameter of the Earth. 1,400 bodies of the size of the Earth could be packed inside Jupiter and leave room to spare. Saturn, which comes next in order, is second only to Jupiter in size, having a diameter of about 70,000 miles. These two are by far the largest of the planets. Uranus and Neptune have each about 4 times the diameter, and so about 64 times the volume of the Earth. The size of Pluto is not yet known with accuracy, but it can hardly be larger than the Earth and is probably considerably smaller. Jupiter and Saturn form such conspicuous objects in the sky that they have necessarily been known from the earliest times, but Uranus and Neptune are comparatively recent discoveries. Sir William Herschel discovered Uranus quite accidentally in 1781 while looking through his telescope with no motive other than the hope of finding something interesting in the sky. By contrast, Neptune was discovered in 1846 as the result of intricate mathematical calculations, which many at the time regarded as the greatest triumph of the human mind, at any rate since the time of Newton. It was a triumph of youth. The honour must be apportioned in approximately equal shares between an Englishman, John Couch Adams, then only 27 years old, who was afterwards professor of astronomy at Cambridge, and a young French astronomer, Urbain J. Leverrier, who was only 8 years his senior. Both attributed certain vagaries in the observed motion of Uranus to the gravitational pull of an exterior planet, and both set to work to calculate the orbit in which this supposed outer planet must move to explain these vagaries. Adams finished his calculations first and informed observers at Cambridge as to the part of the sky in which the new planet ought to lie. As a result, Neptune was observed twice, although without being immediately identified as the wanted planet. Before this identification had been established at Cambridge, Leverrier had finished his computations and communicated his results to Galle, an assistant at Berlin, who was able to identify the planet at once, Berlin possessing better star charts of the region of the sky in question than were accessible at Cambridge. Gradually it emerged that the gravitational pull of Neptune was inadequate to account for all the vagaries in the motions of Uranus, while similar vagaries began to appear in Neptune's own motion. This pointed to the existence of yet another planet, further out even than Neptune. Just as Adams and Leverrier had done on the former occasion, so Dr. Percival Lowell, of Flagstaff Observatory, Arizona, computed the orbit in which the conjectured new planet, Planet X, ought to move, but it was only recently, March 1930, after many years of careful search, that the Flagstaff observers discovered the planet Pluto, moving in almost precisely the orbit which Lowell had predicted 15 years previously. As far back as 1772, Bode had pointed out a simple numerical relation connecting the distances of the various planets from the Sun. This is obtained as follows. Write first the series of numbers 0, 1, 2, 4, 8, 16, 32, 64, 100, 28, 256, in which each number after the first two is double the preceding. Multiply each by 3, thus obtaining 0, 3, 6, 12, 24, 48, 96, 100, 92, 384, 768, and add 4 to each, giving 4, 7, 10, 16, 28, 52, 196, 388, 772. These numbers are very approximately proportional to the actual distances of the planets from the Sun, which are, taking the Earth's distance to be 10, Mercury, 3.9 the Venus, Sil Geom I, Earth, 10.0 Mars, 15.2 asteroids, 26.5 Jupiter, 52.0 Saturn, 95.4 Uranus, 191.9 Neptune, 300.7 Pluto, 400. The law was enunciated before Uranus and the asteroids had been discovered, so that it is somewhat remarkable that these fit so well into their predicted places. On the other hand, the law fails completely for Neptune and the newly discovered Pluto, so that it seems more than likely that it is a mere coincidence with no underlying rational explanation. The outermost planets are at enormous distances from the Sun. An inhabitant of Pluto, if such existed, would receive only a 16th part as much light and heat from the Sun as an inhabitant of the Earth receives. It can be calculated that if Pluto's surface were warmed only by the heat of the Sun, it would be at a very low temperature indeed, somewhere in the neighborhood of minus 230 degrees centigrade, or more than 400 degrees of frost on the Fahrenheit scale. A telescope collects heat as well as light. Not only is the heat-gathering power of a large telescope tremendous, but extremely sensitive instruments have been designed to measure this heat. The 100-inch telescope at Mount Wilson is said to be capable of detecting the heat received from a single candle on the banks of the Mississippi 2,000 miles away. This great sensitiveness has made it possible to measure the infinitesimal amounts of heat received from single stars and planets, and so to estimate the temperatures of their surfaces. Recent measurements indicate that the surface of Jupiter is at a temperature of about minus 150 degrees centigrade, which is just about that at which it would be maintained by the Sun's heat alone. On the other hand, similar measurements assign temperatures of minus 150 degrees and minus 170 degrees respectively to Saturn and Uranus, both of which are rather higher than would be expected if these planets had no source of heat beyond the Sun's radiation. But it seems clear that any sources of internal heat must be quite small, and that all the major planets are very cold indeed. There can be neither seas nor rivers on their surfaces, since all water must be frozen into ice. Neither can there be rain or water vapor in their atmospheres. It has been suggested that the clouds which obscure our view of Jupiter's surface may be condensed particles of carbon dioxide, or some other gas which boils at temperatures far below the freezing point of water. The physical conditions of the smaller planets are much more like those with which we are familiar on Earth. Owing to its greater distance from the Sun, Mars is somewhat, but not enormously, colder than the Earth. Its day of 24 hours 37 minutes is only slightly longer than our own, so that its surface must experience alternations of warmth by day and cold by night, similar to those we find on Earth. In the equatorial regions, the temperature rises well above the freezing point at noon, occasionally reaching 50 degrees Fahrenheit or even more. But even here it falls below freezing some time before sunset, and from then until well on in the next day, the climate must be very cold. The polar regions are of course colder still, the temperature of the snowcap which covers the poles being somewhere about minus 70 degrees centigrade or minus 94 degrees Fahrenheit, 126 degrees of frost. Venus, being nearer the Sun, must have a higher average temperature than the Earth. But as each of its days and nights is several days of our terrestrial time, the difference between the temperatures of day and night must be far greater than with us, so that its surface must experience great extremes of heat by day and of cold by night. The night temperature appears to be fairly uniformly equal to about minus 25 degrees centigrade or minus 13 degrees Fahrenheit. At any point on the planet's surface, weeks of this bitterly cold night temperature must alternate with weeks of a roasting day temperature. Mercury is so near the Sun that its average temperature is necessarily far higher than that of the Earth. It reflects only a tiny fraction, about a 14th, of the light and heat it receives from the Sun. All the rest goes to heating up its surface. A number of considerations make it likely that the planet always turns the same face to the Sun, just as the Moon always turns the same face to the Earth. If so, the unwarmed half of its surface must be intensely cold and the warmed half intensely hot. It can be calculated that in this case, the warmed hemisphere ought to have a temperature of about 357 degrees centigrade. If, however, the planet was in fairly rapid rotation, its whole surface would have a temperature of only about 170 degrees centigrade. Quite recently, Pettit and Nicholson have measured the amount of heat received on Earth from the warmed hemisphere and find that its temperature must be about 350 degrees centigrade or 662 degrees Fahrenheit, thus confirming that the planet always turns the same face to the sun. Its warm hemisphere is at a temperature which melts lead. The other hemisphere, eternally dark and unwarmed, is probably colder than anything we can imagine. Franklin Adams chart. The Milky Way in the neighborhood of the Southern Cross. Galileo's discovery of the 4 satellites of Jupiter was followed in time by the discovery that every planet was attended by satellites, except the 2 whose orbits lay inside the Earth's. In 1655, Huygens discovered Titan, the largest of Saturn's satellites, and by 1684, Cassini had discovered 4 more. Then, after the lapse of a full century, Sir William Herschel discovered 2 satellites of Uranus in 1787 and 2 more satellites of Saturn in 1789. We shall discuss the full system of planetary satellites and also the smaller bodies of the solar system, comets, meteors, and shooting stars, in a later chapter when we come to deal with the way they came into being. The galactic system. Our next landmark is the survey of the stars by the 2 Herschels, Sir William Herschel, the father, 1738 to 1822, and Sir John Herschel, the son, 1792 to 1871. What Galileo had done for the solar system, the 2 Herschels set out to do for the huge family of stars, the galactic system, bounded by the Milky Way, of which our sun is a member. On a clear, moonless night, the Milky Way is seen to stretch, like a great arch of faint light, from horizon to horizon. It is found to be only part of a full circle of light, the galactic circle, which stretches completely round the Earth and divides the sky into 2 equal halves, forming a sort of celestial equator, with reference to which astronomers are accustomed to measure latitude and longitude in the sky. Galileo's telescope had shown that it consists of a crowd of faint stars, each too dim to be seen individually without telescopic aid, see plate for thumb. And, as might be expected, the proper interpretation of this great belt of faint stars has proved to be fundamental in understanding the architecture of the universe. If stars were scattered uniformly through infinite space, we should at last come to a star in whatever direction we looked, so that the sky would appear as a uniform blaze of intolerable light. It is true that this would not be the case if light were dimmed or blotted out after traveling a certain distance, but even then the sky would appear the same in all directions, for there would be no reason why one part of the sky should be more lavishly spangled with stars than another. Thus, the existence of the Milky Way shows that the system of the stars does not extend uniformly to infinity. It must have a definite structure, and it was the architecture of this that Sir William Herschel set himself to unravel. The work he did for the northern half of the sky was subsequently extended to the southern hemisphere by his son, Sir John Herschel. We shall best understand the method employed by the Herschels if we first imagine all the stars in the sky to be intrinsically similar objects. Each would then emit the same amount of light, so that the nearer stars would appear bright and the further stars faint, merely as an effect of distance. The way in which apparent brightness decreases with distance is of course well known. The law is that of the inverse square of the distance, which means that the apparent brightness decreases just as rapidly as the square of its distance increases. A star which is twice as distant as a second similar star appears only a quarter as bright, and so on. Thus, if all stars emitted the same amount of light, we could estimate the relative distances of any 2 stars in the sky from their relative brightnesses. By cutting wires of lengths proportional to the distances of various stars and pointing these in the directions of the stars to which they referred, we could form a model of the arrangement of the stars in the sky. We should, in fact, know the whole structure of the system of stars except for its scale. To represent the faint stars of the Milky Way, a great number of very long wires would be needed. In the model, these would all point towards different parts of the Milky Way, forming a flat wheel-like structure. The problem which confronted Sir William Herschel was more intricate because he knew that the stars were of different intrinsic brightness as well as at different distances, and both factors combined to produce differences of apparent brightness. One of the main difficulties of astronomy, both to the Herschels and to the astronomer of today, is that these two factors have to be disentangled before any definite conclusions are reached. Herschel found that the number of stars visible in his telescope field varied enormously with different directions in space. It was, of course, greatest when the telescope was pointed at the Milky Way and fell off steadily and rapidly as the telescope was moved away from the Milky Way. Generally speaking, two telescope fields, which were at equal distances from the Milky Way, contained about the same number of stars. In the technical language of astronomy, the richness of the star field depended mainly on the galactic latitude, just as the Earth's climate depends mainly on the geographic latitude, and not to any great extent on the longitude. Fields at different distances from the Milky Way were found to differ in quality as well as in number of stars. The brightest stars of all occurred about equally in all fields, the difference in the fields resulting mainly from faint stars, and particularly the faintest stars of all, becoming enormously more abundant as the Milky Way was approached. Sir William Herschel rightly interpreted this as showing that the system of stars surrounding the Sun began to thin out within distances reached by his telescope, and that they began to thin out soonest in directions furthest away from the Milky Way. He supposed the general shape of the galactic system of stars to be that of a bun or a biscuit or a watch, the stars being most thickly scattered near the center and occurring more sparsely in the outer regions. The plane of the Milky Way, of course, formed the central plane of the structure. The fact that the Milky Way divides the sky into two almost exactly equal halves suggested to him that the Sun must be very nearly in this central plane, and this is confirmed by the recent very refined investigations of Sears and Van Ryn and others. From the fact that parts of the sky which were equidistant from the Milky Way appeared about equally bright, Herschel inferred that the Sun not only lay in the central plane of the system, but was very near to its actual center. This view has prevailed until quite recently, but the researches of Shapley and others now show it to be untenable. See page 65 below. Figure 1 shows a cross-section of the general kind of structure which Sir William Herschel assigned to the galactic system, although the detailed distribution of stars shown in the diagram is that given at a much later date, 1922, by Kapteyn. It is easy to see how a structure of this type would account for the general appearance of the sky. Those stars which appear brightest of all are, generally speaking, the nearest. They are so near that no appreciable thinning out of stars occurs within this distance. For this reason, the very bright stars occur in about equal numbers in all directions. The stars which appear very faint are mostly very distant, so distant that the great depth of the system in directions in or near to the galactic plane is brought into play. In such directions, layer after layer of stars, ranged almost endlessly one behind the other, give rise to the apparent concentration of faint stars which we call the Milky Way. Figure 1. The structure of the galactic system. According to Herschel and Kapteyn, the final acceptance of the Copernican view of the structure of the solar system was in a large measure due to Galileo's discovery of the similar system of Jupiter, which was so situated in space that a terrestrial observer could obtain a bird's-eye view of it as a whole. We can never obtain a bird's-eye view of the solar system as a whole because we can only see it from inside, so that optical proof that such systems could exist could come only from the discovery of other similar systems which we could see from outside. Sir William Herschel believed he had confirmed his own view of the structure of the galactic system in the same way by discovering similar systems, of which he could obtain a bird's-eye view because they were entirely extraneous to the galaxy. He spoke of these objects as island universes and believed them to be clouds of stars. They were of hazy nebular appearance, and although it was impossible to distinguish the separate stars in them, he believed that sufficient telescopic power would make this possible, just as it had enabled Galileo to see the separate stars in the Milky Way. These objects, which we shall describe almost immediately, are generally known as extragalactic nebulae from their position, although we shall frequently find it convenient to use the briefer terms great nebulae, to which their immense size fully entitles them. Nebulae. A telescope exhibits a planet as a disk of appreciable size, and an eyepiece which magnifies 60 times will make Jupiter look as large as the Moon. Yet an eyepiece which magnifies 60 times, or any greater number of times, can never make a star look as large as the Moon. No magnification within our command causes any star to appear as anything other than a mere point of light. The stars are of course enormously larger than Jupiter, but they are also enormously more distant, and it is the distance that wins.